Okay, then.
Professor Belfrost's science class is back.
Yep, I'm sorry, a little error on the editing of the video. Okay, so welcome back to my class. And today I will give you another lesson on physics. Okay, so we'll finish up the chapter on kinematics today. Uh, there will be another video about revision on this chapter, but there will be in the next time. Okay, today we'll finish up the materials. Okay, so first I want to review just big concepts. Okay, so first is kinematics. Actually, it is defined as the study of motion without considering its causes. And in order to describe motion of an object, you must first be able to describe its position relative to a convenient reference frame. Mostly we take the Earth, okay, but it may be another stationary object relative to the Earth, or maybe even sometimes you can take some object in motion to be the reference frame, okay, on any particular time. Okay, so the change in position is known as displacement, and the word displacement always implies that an object is moved or has been displaced. While distance, on the other end, it is defined to be the magnitude or size of displacement between two positions. It's very important to note that the distance traveled, however, can be greater than the magnitude of displacement. When displacement is an example of a vector quantity, distance is an example of a scalar quantity. Every measurement of time involves measuring a change in some physical quantity, and yeah, time is very important in any discussion regarding about motions. Okay. Average velocity. Average velocity is displacement change in position divided by the time of travel. While instantaneous velocity is the average velocity at a specific instant in time or over an infinitesimally small time interval. Instantaneous speed is the magnitude of instantaneous velocity, but differently, average speed is not. Okay, it's not just the magnitude of average velocity, they are both different. Okay, so average speed is the distance traveled divided by the elapsed time. Okay, you know that the distance can be different from displacement most of the time, so please be careful. Average acceleration is the rate at which velocity changes. Although acceleration is in the direction of the change in velocity, it's not always in the direction of motion. Okay, another term for acceleration is deceleration. Deceleration is when an object slows down, and its acceleration is opposite the direction of its motion. And another term is quite important to be noted is instantaneous acceleration, or the acceleration at a specific instant in time, which is obtained by considering infinitesimally small interval time, change in velocity, infinitesimally interval of time. Okay, okay, so well done. So let's move to develop some convenient equations for kinetic relationships, starting from the definition of displacement, velocity, and acceleration that has been covered. First, let us make some simplification in notation. So taking the initial time to be 0 as if the time is measured with a stopwatch, for example, then it is a great simplification can be done, since elapsed time is actually delta t equals a t final minus t initial. Then the final time, okay, that means that because the t initial, the t0 is 0, it means that we can just have del t equals t final, okay, the final time of the stopwatch. When initial time is taken to be 0, we can use a subscript 0 to denote initial values of position and velocity. That is x0, the initial position, and v0 represents the initial velocity. And we can put no subscript on the final values because it is clear. Okay, that is t is the final time, so x is the final position, and v is the final velocity. Okay, so del t equals t in this case. Okay, this not if we can take t0 to be 0, only if we can take this into account. It also simplifies the expression for displacement, which is now only delta x equal x minus x0. And also it simplifies the expression for change in velocity, which is now delta v equals v minus v0. So to summarize, here is the simplified notation. Okay, We now can make very important assumption that acceleration is constant. This assumption allows us to avoid using calculus to find instantaneous acceleration. And since acceleration is constant and the first instantaneous acceleration are equal, that is, a is constant, so we use the symbol a for acceleration at all times. By assuming the acceleration to be constant does not seriously limit the situation, we can study in order to grade the accuracy of our treatment. For one thing, acceleration is constant in a great number of situations. Furthermore, in many other situations, we can accurately describe motion by assuming constant acceleration equal to the effort acceleration for that motion. Okay, finally, in motions where acceleration changes drastically, such as in accelerating up to the stop speed and then braking to stop, then the motion can be considered as more separate parts. Okay, then we can take their own consideration at each part. I mean, we can take count the acceleration for each part. Okay, we just need to chop it. Okay, okay, good. So now moving to equations. So we get our first new equation. We start with the definition of the effort velocity. That is, actually, it's better to write the phi bar. I forget the bar here, but it's okay too if you just write the phi. Okay, so phi equals delta x divided by delta t, and yeah, delta x is x minus x zero. So you can have another equation. So you can just doing some algebra and you can get x equals x0 plus vt. And you know the effort velocity actually is okay. Once again, I want to know, I warn you, I missed something here. That is phi bar, not an phi. Phi bar equals phi0 plus phi divided by 2, okay? And this last equation reflects the fact that acceleration is constant. It's just simple average of the initial and the final velocity, okay? And it is very clear from the example that I've given you in this slide, okay? The equation x equals x0 plus vt also gives you insight into the relationship, okay? It shows you, for example, that displacement is a linear function of average velocity. Also, you can, okay, you can notice that also it has linear relationship with t because all of them is not raised to any power, right? So this is just very and you will expect that the graph is just a linear line, okay, going up or going down. It depends on the gradient, right? Okay, so we can now derive another useful equation by manipulating the definition of acceleration, which is a equals del phi divided by delta t. By substituting the simplified notation for delta phi and delta t, it gives us this: a equals phi minus phi o divided by t. And solving it, it yields phi equals phi0 plus at. And the last equation actually gives us some important relationship. For example, final velocity depends on how large the acceleration is and how long it lasts. If the acceleration is zero, then the final velocity equals the initial velocity as expected. And if it is negative, then the final velocity will be less than the initial velocity. Okay, actually, you can get another relationship. I want you to just try to explain by yourself. Okay, it's good for you. And we can combine all the equations above to find a third equation that will be useful, which is start with phi equals phi0 plus at, and by adding the phi0 to each side, then we can get another new equation, and by dividing both sides with 2, then we can get another equation. And but we know that the phi0 plus phi divided by 2 is phi bar, then we can just return it as phi bar equals phi0 plus half times at actually, okay? And by substituting the expression phi bar into the equation for displacement, then we can have another new equation, which is x equals x0 plus phi bar t, yielding x equals x0 plus phi 0 t plus half times a t squared. Very simple. Okay, and from this last equation, we can also get another insight. For example, that displacement depends on the square of the elapsed time. When acceleration is not zero, and if acceleration is zero, then the initial velocity equals average velocity, and it will become a new equation, which is x equals x0 plus phi 0 t as expected. Okay. Okay, done with the third. Now move to the fourth equation that you can get from previous equations. Okay. So if we solve phi equals phi0 plus at, then we actually can have another equation when we want to obtain the t. where is t equals v minus v0 divided by a. And by substituting the previous equations that I have gotten, okay, we have obtained that we can have this new equation: v squared equals v squared plus 2a times delta x with a constant a. And this equation again gives us some insights. For example, the final velocity depends on how large the acceleration is and the distance over which x. And for a fixed deceleration, then a car that is going twice as fast actually doesn't simply stop in twice as distance because it takes much further to stop. As you see that the fee is squared, okay, so it'll take much more extra things to stop it, more time to yeah, more distance, much more distance to stop. Okay, so in summary, here are equations that we have learned so far. You may take a screenshot of it if it is necessary, but if you have written in your notebook, then you are okay with it. Last discussion, important in physics, falling objects. So falling objects form an interesting class of motion problems. For example, when we can estimate the depth of vertical mine shaft by dropping a rock into it and listening to the rock when it hit its bottom, and applying some kinematics that we can examining some interesting situation, can learn actually how gravity works in the process and what we expect from the result and more. Okay. The most remarkable and unexpected fact about falling objects is that if error system and friction are negligible, then actually in any given location of uh, object, it will fall toward the center of Earth with the same constant acceleration, and also at the same time it will land on the Earth, independent of your mass. Okay, but yeah, maybe in the Earth we will rarely expect these things to happen. Maybe we can only expect it in a certain laboratory that is designated to be vacuum. Then you can do the experiment that we will expect this result to happen. Okay. Okay. So air resistance opposes the motion of an object through the air, while friction between objects, such as for example between clothes and a laundry sheet, or between a stone and a pill into which is dropped, also opposes motion between them. Okay. But this will not come now. It will be our discussion for later. Okay. The force of gravity causes objects to fall through the center of Earth, and the acceleration of free falling objects therefore called the acceleration due to the gravity, which is actually represented by a unique symbol, which is G, and G equals 9.80 meter per second squared. Okay. And actually it varies depending on the geological formation and local topography, but we actually really need to take into account for this. We can just use the average constant, which is 9.80 meter per second square. Okay, and the next thing that is really important to be noted is that how we take granted for the sign when we use the positive or the negative sign. Okay, this is very important in our calculation, and it will give us different result if we wrongly use the sign. Okay, so for example, if we define the upward direction as positive, then because gravity will oppose it, then it will be negative. But if we define the downward direction as positive, then it will, you know, that it goes in the same direction, then the gravity will be positive. Okay. Actually, that's the important things I think. And here are the recap for the kinematic equations for object in free fall with acceleration a equals minus g. Okay. This is if we all consider that the motion outwards will be positive. Okay, so it take the gravity to be negative. But if you want to do the other way, as I will show in some of my discussion on problems later, it is also fine as long as you stick on that convention that you have made. Okay, good. Now the last part is graph. Graph is very important because it's not only showing you numerical information, it also reveals the relationship between physical quantities much faster than you can understand it directly when you just see being given that graph to you. Okay. So first note that graphs in this discussion in this video will have perpendicular axis, one horizontal and the other vertical. Okay. So if we have two physical quantities plotted against one another, then most of the time, horizontal axis is to show the independent variable, and the vertical axis is to show the dependent variable. Okay, I will have a straight line graph, then it will be expressed in a general form, which is y equals mx plus b. I know that you have got it in a mathematics class. So actually, this is very basic. So m represents the slope or the gradient, and b is for the y-intercept, and we are done actually. The next thing is actually just the another expansion on that basic concept we have learned. Okay, first one is graph of position versus time for a equals 0 or v equals constant. Okay, so here's just the example. You need to this later. I will give you example on this in the discussion of the problem. Okay, so you see the relationship between the dependent and independent variable by substituting all the value with the variable with the suitable value, that we get new equations for this. We now have x equals vt plus x0, or can be arranged to be x0 equals vt. And yeah, you have got this from our previous derivation, but actually graph can show you the same thing, right? And please notice that the slope of the graph of position x versus time uh, is actually just the velocity. So the slope is just the velocity if we plot the position relative to time, okay, versus time. Second is graph of motion when a equals a is constant but a is not zero. You can see that the position relative to time, it doesn't grow linearly, but it grows to like quadratic, and that's what we expect because yeah, from the derivation we know that uh, it is it has a relationship that is not like x equals 3t. Okay, we have another thing, we have x equals 3t plus half times at squared. So we expect that the t square take the graph to be not linear. It's very important to note that things. Okay, and again we know that the change of velocity relative to time, that's acceleration a. Okay, and we have built another equation from the graph, which is v equals v0 plus at. And this is all not accidental because actually we can derive each of the formula we have gotten so far from from the graph given. Okay, I want you to read the slides that have been presented by yourself because I'm not that okay. You can just read it by yourself to learn more. Okay, I'll not explain one by one because I think the slides shown you very clearly. Okay, now third is graph of motion where acceleration is not constant. Okay, so please pay attention to the figures, and you see that yeah, the slope of the graph at every point, it is different. Okay, and we need another graphical analysis to describe a specific and general characteristic of kinematics when we are facing a is not constant. Okay, we are done with the theoretical things. Let's finish up with the practice on, because it's the most important thing in physics is practice with many kinds of problems. Okay, first, a commuter train travels from Baltimore to Washington D.C. and back in 1 hour and 45 minutes. The distance between the two stations is approximately 40 miles. So what is A and what is B? Okay, A is average velocity. So because it is x final equals x initial, then the train up uh, then the average velocity must be zero because the displacement is zero. And how about average speed? Average speed is just distance divided by time. So you just need to do some, you need to apply some conversion factor, and you're done. You got the result 20 meters per second. Number two, a racehawk coming out of the gate race to the velocity of 15 meters per second US in 1.8 seconds. Now, what is the average acceleration? So, the first step I always remind you to do that is to sketch and assign appropriate coordinate system to best visualize the problem in physics. Physics is full of graph and it is like mathematics too, okay? So you need to have a very clear visualization of what you're trying to solve in this problem. Okay, so here that I have presented you with a suitable graph for sketch of graphs and the coordinate system we use in this problem. Okay, so first we identify the knowns and then find the change in velocity, and then we just need to plug all the known values, the delta p and the delta t, to get the a. Okay, so a equals minus 8 and 3 meter per second. Okay, so there's the average acceleration, and here the negative sign indicates the acceleration is toward the west, as what we have yeah, we have done in the convention that we have written so far. Okay, number 3, what is the average velocity of the train that is shown below if it takes 5 minutes to make its trip? Okay, so please pay attention to the final position is 3.75 kilometer relative to 0 coordinate of x, and the initial x is 5.0, I'm sorry, 5.25 kilometers relative to 0 position or O position, initial position. So the delta x equals minus 1.50 kilometers. So we have done for the displacement is second step, and we have also identified the knowns, which is the x final, the x0, the delta t. Then can solve the average velocity and convert the units to proper units, and we can express it, for example, to be minus 18.0 kilometer per hour. And negative actually means that the motion is too. Okay. That number 4. A jogger ran down the straight stretch of the road at an average velocity of 4 meters per second for 2 minutes. What is his final position, taking his initial position to be 0? Now, first is always to do sketch. Yeah, that's important for beginners. Okay, sometimes I will not do sketch again in my advanced discussion, but I'll always remind beginners to do sketch because that's important. Okay, so we need to pick the proper equation. Here is x equals x0 plus v bar t, and then identify the knowns, enter the known value into the equation, and tada, we get the x to be 480 meters. And velocity and final displacement are both positives. It means that they are both in the same direction. Number 5. Dragsters can achieve average acceleration of 26.0 meters per second squared. Suppose such a dragster accelerates from at this rate for 5.56 seconds, then how far does it travel in this time? Oh yeah, once again, I want to remind you about using the significant figures in physics. It's also taking a quite important role in physics. Okay, so you see from the problem that I've discussed so far, though maybe sometimes I slip, I don't tell you the exact value. For example, that I missed the 0, I don't say the 0 at the ends, a trail 0. Actually, it's very important to pay attention that all of problem need to be represented by the suitable significant figures that assigned in the problem. Okay, as for example, actually, you can just say 26 meters per second square, but because the acceleration, the time is given in three significant figures, we need to consistent. We want two significant figures or three significant figures. How we express um, it in physics is very important. So because we take three significant figures, for example, we need to stick on three significant figures whole of our solution layer. So we'll pick three significant figures. If you want to express in two significant figures, be consistent. Two significant figures along the way in solving this problem. That's very important for me. Okay. Okay. So as usual, first is to define the proper equations. Then identify the knowns and just plug the known values into the equation. And done. We have gotten the answer. Because we have know the initial position and the velocity initially are 0, then it can just simplify to be x equals half times at squared. and then 402 meter. Okay, it's very close to 1/4 of a mile. Okay, number five's done. Now move to number six. So on a dry concrete, car can decelerate at a rate of 7 meters per second, whereas on wet concrete can decelerate at only 5 meters per second square. Find the distance necessary to stop a car moving at 30 meters per second on dry concrete. On wet concrete, repeat both calculations. Find the displacement from the point where the driver sees a traffic light turn red. Take into account his reaction time of 1.5 seconds to get his foot on the brake. Okay, so first again, do some sketch. Yeah, very important. Okay, now start to find the solution to one by one question we give. So for A, we just need to identify the knowns first. Then we are looking for the displacement. We identify the equation that can best suit this problem. And we can use this equation, v squared equals v0 squared plus 2a times delta x. Then we rearrange the equation to solve for x, like shown in the slide. Enter all the known values, and we expect it will yield x equals 64.3 meters on dry concrete. Again, this is three significant figures, okay, as what the problem indicated us to give. Okay. For B, actually, it's not that different. Okay, we just need to change the value, and we expect the value to be 90.0 meters on wet concrete. And for C, actually, first is also re-identify the knowns and what we want to solve for. Okay, so the knowns have presented in the slide, and we want to solve x reaction. Then identify the best equation to use, and now the equation that best fit in our case is x equals x0 plus p bar t. Then we just need to plug in all the knowns to solve this equation, and it will bring us 15 meters. Okay, so 50 meters is while the driver reacts. Okay, it will make the displacement to be 50 meters greater than what is we can react it instantly. So how much displacement they need to prepare? Okay, that is the braking and the reaction added together. Okay, so when dry, it will give us 79.3 meter, and when wet, it is 105 meters. Okay, so please be very careful. And actually, this problem is quite good to show you that you need to prepare for something that you cannot just eliminate in real life. Okay, because you have what called reaction time. Okay, number seven, problem seven. What happens if the person on the cliff throws the rock straight down instead of straight up? To explore this question, calculate the velocity of the rock when it is 5.10 meters below the starting point and has been thrown downward with an initial speed of 13.0 meters per second. I think this is related to another question. Actually, we have no difficulties to find it, even it's related to the other previous question, because it's quite independent. Okay, since we take up is positive, then the final position of the rod will be negative because it will finish up below the starting point at y0 equals 0. Okay, and the initial velocity is downward, therefore negative, and acceleration is also negative due to gravity. Okay, so we expect from the final velocity to be negative too, since the rod will continue to move downward. The first thing we need to do is identify the knowns, then choose a suitable kinematic equation, which is v squared. Actually, I mistyped the equation again this time. V squared equals v0 squared plus 2a delta y. Okay, and then just entered all the known values into the equation, and it gives us v equals minus 16.4 16.4 meters per second. Why we take negative? Because it indicates the rock is heading down. Okay. So though both is acceptable, plus minus, we need to take the one that is rational, that is logic. In this case, it is negative. Okay. Okay. So number 7. Actually, I've been shown in the previous slide. Yeah, I want you to pay attention to that. Read it by yourself. Actually, I'm not very good today. Yeah, that's the discussion for this time. And here exercises for you. They are of two degree of difficulties. The first one is easy. The second one is intermediate level. Okay. I want you to just take screenshot on it and solve it by yourself. If you have any question, please don't hesitate to tell me. I will make a video dedicated to discuss about the problems that I have given. I've prepared it actually. It's actually not difficult for me to just share this solution to the problem. Okay. So yeah, we have done with this lesson. Thank you for have been following so far. Now here's another quote for you for today. So Alan W. Watts once said, "The only way to make sense out of change is to plunge into it, move with it, and join the dance." So thanks for watching once again. Subscribe, give a like, comment, and share this video. I'll be back on Tuesday and Thursday, so keep watching and be thoughtful. See you on the next video. Bye.